Welcome to a new test and teardown video. This time it's a Dymec DY-5731 X-band signal generator. There's actually a little funny detail about the Dymec logo. Look at that one. Now it looks a lot like HP. Yeah, of course, it is an HP company. And they're manufacturing this as a special brand. As far as I understand, they're doing custom products. So this is a custom designed and custom manufactured product. And this is why you can't find anything about this unit online. So the X-band signal generator is a signal generator that can do all sorts of modulations, pulses. So I would expect this to be like a radar simulator with the different pulses here and the rates and stuff like that. The frequency range goes all the way to 10 kilo mega cycles. Don't you just love that? So that is of course 10 gigahertz. And it starts, I think it was 8.6 gigahertz. So that is the frequency range. So there's a magnetron in this unit, and you adjust there's a power feedback, a power measurement bridge, and then you adjust. Here is a mechanical coupling, and then you adjust for 0. So this is the feedback point you adjust. See the output attenuator. This is a mechanical output attenuator that is connected directly to the output. And then it goes to the attenuator. The attenuator is actually a 2-step attenuator. And look at that. Is this really true? Plus 24 dBm output. That is quite a lot. And this attenuator is really easy to turn. Signal all the way down to -76. I really like the way this is made. The way that this curve. How the heck is that done? So this black, I don't know exactly. Something here is moving up and down, right? That is really nice. Got some sync, internal and external, FM, amplitude and phase. We can modulate, yeah, internal and external. I'm actually only interested in continuous wave. It's going to be a little bit interesting how to connect to the waveguide. I don't have a waveguide pickup yet. It is actually on its way, so I'm not sure. I'll just gonna take out a little wire here and just make a very short little pickup to a connector or something like that, so we can measure the outputs. It just in case it is not going to explode when I power this up. I did already take this out of its case to inspect it a little bit. This unit is huge. This is my foot. I can tell you guys, this instrument without its case, it is 32 kilos. And I think it was 11 kilos for the case and the inner cabinet and the side shields and stuff. So you can imagine when everything here was assembled, it was very, very difficult to carry in here. So this is why we're still on the floor. Let's look inside this fantastic unit. As you can see, it is tube based, of course. I believe this is around 1960, plus minus a little bit. I took off, there was a plate here and a cover as well. So now we can see what is in here. And this is, of course, the magnetron. That is the thing that is interesting. If we look down here, that is the magnets. And that is the output. So this is the frequency adjustment. See, here's the dial. So if I see, it doesn't matter if there's a lot of slip slap in this one, as long as there's no slip in the readout. You see, here's the / anti-slip system. So you can dial in the frequency real nice and accurate. So in here, it actually adjusts. See? That was all the way one end. This is all the way to the other end. So that would be only a few millimeters it is moving. But of course you don't need to move that many millimeters when you go from 8.6 to 10 gigahertz. So that is the thing that moves in here. I believe there's something in here that moves under here, that goes in the resonant chamber. That will be in that very point in here. I also think this is the filament, or the filament connections, and in here we will have coils. So that would be a DC feed through filter. All that is probably just, if we it's probably only that all the way into this metal tube. So if I remove this screw, we're probably gonna see two pins sticking out of some glass. I'm probably gonna look at that later if this thing works. If it blows up, yeah, we're going to see this anyway. And I guess this will be the anode connection. And again, there's probably coils and capacitors in here. And that will be the anode. And I believe the chassis is probably the ground for the high voltage part. So this anode supply goes to that switch. And look at the mechanics. Isn't that just cute? So that is, of course, all the different modes where the anode goes, because this is how you modulate whatever it's doing. It is doing it on the anode supply. So that means the anode can go all sorts of different directions in this unit, and one of them will be this modulator. And this modulator is, I think this is always connected to the anode supply. And this pot here, this really large high voltage pot meter, is of course always, see, a thing. Because when you change frequency, you need more or less anode voltage, so you have the same output power, or something like that, right? So this got to be connected to that one. Definitely some high voltage stuff going on here, and there will be a frequency compensation of something that controls the anode, so it can switch on and off real fast. And here we can see the tubes. Where's that one? Here it is. Oh, and we've got some diodes as well. Oh, that's nice. So that would be the modulator board. Oh, and we see some fancy stuff down there. That is actually the attenuator. This is the waveguide that connects both ends of the attenuator. I will show you a lot more of that in a second. Just look at all the capacitors, and they are kind of rotten, by the way. They smell like old mold, so I'm a little bit worried about powering this up because of that smell. Oh yeah, look at that one. We've got a big fat transistor here as well. So I also believe all those tubes that will be related to power supply. We've got a lot more power supply parts over here. Oh yeah, and that will be the power detector, by the way. See, this is the output from, oh shit, that was, damn it, magnetic. Oh fuck, I got a shock. Sorry about that. So there's a power splitter here, and that will be a load at that end, and at that end it goes up to the power detector. It's probably just an NTC that gets heated up by the output power, and that is used to control the feedback and the power systems. We can't really see the other output. It goes down here. But let's look at that one here. I think this one is the third transformer, and that one is used via that diode and a current limited resistor, limiting resistor to the high voltage supply. I don't like that kind of corrosion and stuff here. So that, I think I need to look a little bit. Maybe I need to clean up here. Where are those wires going? But that would be the high voltage supply, because look at that capacitor. I think this is 4,500 volts DC. So that is a nasty one you don't want to touch. And look at the distance to metal here is just almost nothing. So that is not so smart. So I think we need to move. This one is the high voltage. We need to move this a little bit away from the metal. When I got this one, I saw some tubes that was broken. That tube was broken in half. I actually got it up here, and that tube was completely white, so I replaced that one. I'm a little bit worried about the voltage regulator, that one, and that is an OA1, or is it an OA2? I can't remember right now. Yeah, okay, look at that. Let's just take it out and have a look. It's an OA2, so it's 150 volts. And I'm a little bit worried about the way that this looks. But what I did is I tested this tube with my neon tester, and it actually lights up. So there is still gas in this one. I just don't know if it's accurate or not. So this will be the voltage references. See, we got some more voltage regulator tubes down here. No, they're not. They're just tubes running red hot, I guess, right? Why are they so black? Anyway, now we got all the tubes okay in that power board. So those two will be pulse units. See, this is pulse A, and the other one here is just pulse B. So I think it doesn't really matter if they work or not if I'm only using the CV mode. And that could explain the previous owner, the donator of this unit actually said it worked. And yeah, this one was completely white and this one was in 2 halves. So I think it was only tested in CV mode. But anyway, I'll try and get a new one here as well, just so we can test all the different pulses. I don't know if I will cover all these details in this video, because I'm afraid it's going to be very, very long. And you see those two modules, they look very, very much the same. Maybe they're doing exactly the same, right? Yeah, they're so much the same. And note one little cool detail about the different PCBs. They're different sizes, so you can't really mix them up. All 4 PCBs different sizes, so that is really nice. So this is the back side of the unit, and I believe this is my mains entry transformer, and that will be another transformer as well. And that is of course the back side of all the capacitors and voltage regulators and pulse controlling power tubes. They located all the power components close to the fan, and that is very, very smart way to do this. We got a lot of diodes, again close to the fan, exactly how you would do that. Power resistors, again in the airflow. So this is of course optimized for good thermal. Yeah, coax cables for the pulses. Pretty smart. And this is of course the bottom view. So in here is the attenuator, and it goes super, super smooth. There's no friction at all. So remember I showed the output from the directional coupler here, and it goes up here and through the 2-stage attenuator and out. So that is the signal path. And down here we see, what is that? So that is actually transistors on the bottom of the thing that I thought was a transformer. See that down there? So that is probably the high voltage oscillator. Really? How nice! I did not expect that, really. But that is what 2N. Can we zoom in? Can we probably read that? You're real smart. Let's see if I can get this in focus. Come on. Is it that wire that is annoying? Okay, I give up. It's not that easy. Oh yeah. Look at that. Cute. Ah, come to Papa. Oh, this is tough. Yeah, I gotcha. That is, yes it is. It is indeed a delay relay. That is so cool. So the way this works, you can see the heater here. So there's a filament you heat up, and then there's a contact up here. So this is a bimetal. So when you heat this up, it's gonna bend and then create a contact. That is really, really nice. And then we got a, you can really see the rotten capacitors here. I think somebody left this one is in a really wet, damp place for a long, long time. Look at that. Ugh. That is gross. And we got some diodes here. I actually took one of them out and measured. Those are 1N1084s, so that is 400 volts, 500 milliamps, as far as I remember. And the other, there in this bridge, they are not exactly like that when I measured them. So that is really, really weird with the forward and the reverse voltages. I think it was 1.7 in one way and half a volt the other way. And those are about half a volt in one way and nothing the other way. So why are they? That is, I don't know what that is really. I think we're gonna power this up in a minute and see if it actually works. So that will be the tubes, the defect tubes. They were in the unit when I got it. This label fell out when I opened the unit, so I think this is the power sensor. I think this is maybe an NCC power sensor, right? I think I'm ready to power it up. I just powered, this one is on. I am going to dial up slowly the voltage on my variable here. And then we're going to see what happens. Because that is 100 volts and 40 watts. 120 watts and 41 watts. And I don't see any glow anywhere. Let's turn off the light here. And then I just crank up the voltage. Real slow. This is 180 volts and power consumption is 88 watts. Ooh, I see glow now. This is real good. 220 volts and look at that. We got light in all the bulbs. Whoop. The fan is running. That is 250 watts now. Why the hell didn't that? Ooh, I got a big shock. But anyway, the fan is running. We got light in everything. Now let's see if there's any output. So now I'm going to power it up with a spectrum analyzer connected to it. And I set the, well, let's turn off the light here. Set a 9 gigahertz and a span of 1 gigahertz. And I dialed this one to 9. Minus 10 here. Let's just be real low practical here, right? Let's see what happens if I do like that, right? So let's crank on the power and see what happens. So we see some light in the lamps, and when the fan goes on, hell loose is gonna break. Why don't the fan go immediately? I find this a little bit worrying. Did I select CV mode? Yes, I did. And I don't have any thing here. Now the fan goes. Yeah, look at that. I see some power here. Yes. I see power here, right? But I don't see anything on the spectrum analyzer. That is a little bit worrying. So let's dial the attenuator. Probably the other way, right? Why don't we see anything? That is not good. Damn it. But this one seems to be working. I bet there's output. So where is the... I have to go back in a second. Nothing works here. Oh, what a night. Now I'm measuring around here. I've removed this metal bar here. So now I got a lot easier access. I believe this is the switch mode high voltage generator, but it is actually oscillating, but I don't really get any high voltage. So maybe I got some dead diodes or a shorted capacitor or something like that. So that could explain why I don't have any output. I still see the magnetron gets quite hot, but I believe that is the filament that heats up everything here. So when I turn off power, I can just touch the metal here because everything here is ground. So it should be fairly safe to touch the metal here. And then I can feel that it is nice and warm. So now I have removed this little plastic holder here. And now I got access down here. I believe this is the anode or some part of the high voltage. Most likely, right? Why would it else be like that, right? But normally on magnetrons, the high voltage is a negative supply on the filaments. So that could also be what I need to measure. I don't have any schematics at all, so I'm kind of just trying my way through this. But now we'll try and measure the high voltage on that point. Also, I should be able to measure some high voltages on those wires, right? I got a scope here with a probe that can handle lots and lots of kilovolts, so it should be fairly easy just to scope around here. So I just measured minus 700 on that point, and that will be my filament connections. Most likely also chassis connection. That will probably be the last one of the 3 pins, because I only got 2 wires in this system here. I can't really get this out. I can't really access those wires. So that is a little bit annoying, because I would love to know the DC potential here, because I was expecting quite a lot more than 700, but that is what I see so far. I got 700 on that one, and I got minus 700 and minus 1000 on that one. So obviously we've got some amplifiers and stuff here, and that will probably change the voltage on the magnetron depending on the frequency, because when I dial the frequency, this pot will change. So that is how I think it works so far. So good. Yeah, not my lucky day. That will be the two filament wires. I traced them all the way down here. And yes, we got 6.1 volts between those two wires, and also a potential of about -500. So that will be the cathode, and I expect that to be -500. That's perfectly fine, but I would expect the anode to be plus a few thousand, at least when it starts and stuff like that. So yeah, we don't have any kind of high voltage across the magnetron, so that is why we don't have any output. So where's that voltage? You are not going to believe this. Okay, this entire unit here, this thing here is big as a brick, and probably way even more, by the way. This big thing is like a switch mode converter. There is a there's a transformer and switch transistors and stuff in here. I've shown them from the other side. And this capacitor is of course not a high voltage, but a low voltage capacitor. So 4,500 microfarad, 35 volts. That's what we got here, right? So this unit, what this is doing is, when you give this 22 volts a negative, by the way, so this is of course what I'm trying to do here, and out comes 71 volt RMS and 42 volts RMS in reverse. Okay, and look at the color codes. Those two color codes here, those two output wires, if you follow the wires down here and all the way down there at the bottom, out that little hole, and here we go, they go only to the fan. Isn't that just cute? Because the fan is a 50 to 60 hertz, 115 volts or whatever it is, right? So of course, to drive this fan, you need this big thingy. And if you don't believe me, listen to that. Here we go. And that is the 22 volts. And 17 watts. So it's a really good switch power supply size, mega size. Yeah, I love it. Oh yeah, did I forget to show you guys this? So the bulb is of course also broken, but look at the isolation distance to chassis. I'm not super happy about the distances here, and by the way, it was really difficult to pull this out. Something quite funny about this, I don't know if you can see this, but this plastic is like, I don't know if I can show you this, but there's really no more light coming through this anymore. So that's weird. Oh yeah, there was another thing I really wanted to show. So this is the directional coupler, and of course over here is where it measures the power and all that, right? But look at that. So it's also measuring the temperatures on both sides using two NTC resistors. And that is of course also in the compensation loop. The temperature. That is of course important. Yeah, that will be the super cool attenuator. I really would like to look inside this unit, but I don't think it is going to be that easy to open. Oh yeah, I don't know if you can see this. See if I turn the attenuator. Can you see the wire? I don't know, let me see if I can get some better light. Maybe here? Yeah. Here we can see it. See, the wire is coming out through a hole. And this is the wire that pulls this white scale up and down. Why is it so bad to focus? I love it when they have these super cool mechanical solutions. So this is the first modification I made to this unit. See this big unit we had here? That one is only the fan power supply. I cannot hardly lift it like this without cutting my fingers. It's just really heavy. So yes, this is a switch mode power supply, made the good old style. And of course you don't need this at all to run the fan. That's so stupid. All you have to do is connect the wires to the fan. It is a 115 volts fan to the center tap of the first mains transformer, and then the fan will run just fine. All right. Meanwhile, a nice a person called John posted finally a picture revealing the voltages needed for the klystron, and now I know that I need plus 500 volts of anode, and I got minus. So that means there is definitely a high voltage I am missing, and that is of course why I have no output. I got a negative 400 on the anode, and I also got about minus 400 on the cathode side. The filament and cathode relative to chassis, that is the cathode as far as I know. And so now I'm going to take an external power supply, of course an old one, and connect and see if that works. So this is a 1 kilo ohm series resistor. This is because I don't want to overdrive the current, and I want to be sure that I'm doing this right. So this is going to be interesting. Let's power this up and see if it works. Oh yeah, just too bad with an external power supply, and I can actually measure the current and everything here, and I do get about 60 milliamps at 500 volts. So everything looks like it's right. It is really using the right amount of current and voltages and stuff, but there's just absolutely no output. So why is that? I don't know, but that means my time is kind of over searching for the problem in the power supplies and all that. Okay, they don't work, but much more important is that I don't have output. So I think this video actually needs to stop here when it comes to getting output, but I think I will disassemble it some more, and I really would like to look at the attenuator and the output here and stuff like that. I don't see I can find any errors here, but it's still really fun to see how this is built. So that is what I wanted to play with the next few hours. So hang on if you want to see a little bit more. So this is the anode connection. It is really beautifully made. I believe there is a feed-through filter in here, most likely, right? And here it is in all of its beautiful glory. It was not that easy to pull out, but I am sorry to say that I think it does not work. Maybe it has something to do with this tuning system, and probably something in here is all the way down and shorting this little resonant chamber that is kind of in here, right? Maybe it's a mechanical problem. It looks like somebody tried to lubricate it or whatever. But at least this is how it looks like. I'll be careful not to drop it. This looks a little bit weird down here. Like it's cracked around here. But it is actually pulling correct anode currents at the correct voltage. So why the heck is there no output? But that is just probably the way that it can fail too. So let's look a little bit deeper down this machine. Now we're looking into the magnet and down the exit. So there's a nice little spacer here. Oh, that's actually really heavy. Why is that so heavy? So it's made of brass or something, or copper. It is crazy heavy, this one. Also, I really need to disassemble all this, but carefully, because if I find like a broken part or something here, this little reverse coupling thing that is in here, right? So if this is broken or stuck, or if the attenuator is broken and stuck in here, and that could be the reason for my missing output, of course I want to sample everything again. So that is why it's important to video document every little detail I do. And maybe if somebody else needs to repair and restore one of these one day, we will have the information documented. So just fast forward if you find this boring, but that is just the way it is. That was difficult to get this unit out. And it's really mounted in a million of ways and screws and cables and stuff. And I did carefully leave a piece of the correct wire with the correct color codes. So I will be able to restore this. It's going to be a little bit difficult, but I was hoping to find something that kind of fell down or is broken or is missing or is wrong in here somewhere. Maybe in the attenuator or something. But there's the only way to figure this out is to actually open everything and see if we can figure this out. Of course, the tube itself could just be broken. And then there's nothing I can do anyway. Oh yeah, by the way, see? This is where my missing label would fit. That one we talked about earlier in the video. That is where it was, thermistor mount. So this is definitely the power sensor. Here we can better see. I really love the way this works. That is so cute. With this little wire that pulls it. And so there's probably a spring. Yeah, definitely. Oh, that is just the coolest. So I mean, if everything fails, this is just a super nice souvenir. I love it. So now we're inside this unit with the output attenuator. Well, this is actually the power level pre-adjustment. And if you look at that part, this one can rotate when you turn the knob down here. And this one rotates in the hole. Isn't that just an amazing way to create an attenuator? It looks like it's transparent, but I think it's just because it's reflections. Really a beautiful unit. So no, I don't find anything wrong in this one. Now I want to see if I can get in here, but then I realize, look at the screws. What, I need to access them from the inside here? That is impossible. I need to build a special screwdriver to handle that. Damn it. I think you really need to see, oops, the directional coupler, how that works. It is absolutely interesting. So this is where the power meter was located. And you can just look straight through it. I think this is just an angle. Alright. But the magic is in the two crosses you see up here. This. How can I show you guys this? I need some light. Hang on. Here we go. Down here we can see the two crosses. And that is because the way that the waves travel inside the guide, it kind of hits this area or that area depending of the direction of the signal. Isn't that just crazy? And then, because there's an opening here, now only that signal that comes from one end goes out, either this side or that side. Just like they show here. Huh. I think that is so amazing. And that end, that is a load, by the way. So this material you see down here is actually absorbing the power. Let's have a closer look on the two NTC resistors. They're 820 ohms, both of them. It looks a little bit like it's different part numbers or stuff like that, but they measure the same resistance, more or less. Maybe they got different characteristics. Somebody called Sam was here. That's funny, a little secret message. But this one is what I really wanted to have a look at. So this is the attenuator. And look what happens here about the polarity of the signal. And then it goes out up in a, it looks like it is round. And here it is round. And then it goes flat again and out. And then when I crank the attenuator, both of the two halves, they rotate. Just absolutely amazing, this hardware, how well this is designed. But this is how you make an attenuator for 10 gigahertz, covering this huge area or huge range, minus 76, and this accurate. Look at that. Plus 24, right? So it's a huge span, and I believe this would have been super accurate back in the good old days. See how easy you should be able to set it to minus, plus 10, and then 19, la 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 la. I mean, I think this is definitely a keeper. This unit, super beautiful. I really would like to show you guys how how it really works, but I think it works a lot like this first power coupler I showed you that rotates in here. So I think there will be a gap here that swap this into a tiny little line, and then there is another one in here that rotates, either kills the signal or passes it straight through. So there will be a thin piece of metal or piece of some special thing in here that does that. I think if we unscrew those, we should be able to have a look at that part. Here we go, and this is exactly what I wanted to show. See this thin, it's like almost made of glass, but I think it's this special ceramic material. And look at that one. So this is to control the polarization. And when this one aligns this way, like horizontal, just like the other one is right now, in here there is a matching, I don't know if we can, why can't we see that? But there is definitely in here a matching one, and this is the lowest attenuation. Of course, this is the pass straight through, and the more you want to attenuate, you move it up like that, and then you completely kill the signal because it's horizontal vertical, and that means nothing passes through. Isn't it just amazing? And they splattered some white silver stuff here that's kind of conductive. I don't know, silver grease. I don't know if I can show you. I hope I will be able to assemble this again. So this is the power detector. I don't know if you will be able to see this, but this tiny little black drop you see down there, let's see how close we can go. That one down there, that is actually an NTC resistor. The wires to it is like thinner than a hair. Let's go in macro mode. Here we go. That is a tiny NTC. Wow. Well, let me show you the load. So this piece of ceramic is actually the load. Isn't that just fantastic? So it picks up the signal and it just dissipates all the energy as heat in this ceramic. It isn't electrically conductive, but when you come with 10 gigahertz, it will act as a 50 ohm load. Isn't it just amazing? And it fits. Like they grinded it down to the last tenth of a millimeter or something like that. See how well it fits? Like that. And then the screw here goes into the load, and this is a thick piece of copper or brass that is tinned or silvered. It is super heavy, and this is of course to keep the temperature stable here. I forgot to add this little detail here about the magnet. Let's look a little bit on the magnet itself. It is really big, and it is also very powerful. You get a big shock when you go near it with some stuff. But look at that. Isolator. And there's an input and there's an output. So this is what it does, is it isolates the RF signals from the klystron. So it's not a magnetron, and the magnet has nothing to do with the way this unit oscillates. The magnet is only an isolator, so power can only go one way and not the other way. And that is also why this output power range selector here, when you flip this, you're going to block the signal from getting out. Of course it's going to go back, and it's going to interfere with the klystron if you don't have an isolator mounted here. So that is why they got this fantastic magnet here. Oh, this is heavy duty.